Hello students, in this video session I am going to discuss about one of the important concept in the chapter electrostatics. So the subtopic I am going to deal today, that is electric field and potential due to uniform charged sphere. Uniform charged sphere. These are two types: conducting charged sphere, non-conducting charged sphere, and hollow sphere, nothing but shell, and solid sphere. This is one of the very important concept. 90% definitely there will be a question from this concept. Either you take state level engineering entrance exam or medical entrance exam to national level engineering entrance exams or medical exams. Definitely there will be a question from this chapter and from this sub concept also. So this is very important. Now we'll start. First, let me talk about electric field due to the uniformly charged conducting sphere. Uniformly charged conducting sphere I am talking about. What is a conducting and non-conducting material first? The difference between conducting and non-conducting material nature wise, the material wise, for the conducting material, whatever the charge you have given to that material, that conducting material resides only on the top surface. No charge can go interior to the material. Let us suppose you have taken a sphere, you have given charge, conducting sphere, you have given charge, either it is shell or solid sphere. In both the cases, if it is conducting material, if it is conducting sphere, whatever the charge you have given, that resides only on the top surface. But in case of non-conducting sphere, charge availability of the free charges inside as well as the top surface also. That is the difference. Now first we'll discuss about the electric field due to uniform charged conducting sphere. Let me take one sphere whose radius is r, to which I have given charge q, Let me calculate electric field inside the sphere, inside the solid sphere. This is conducting hollow sphere and solid sphere, both one and same as long as it is conducting, right? Because anyway charge resides only on top surface. Inside nothing but distance is always measured from center, so the distance is less than of the radius. Where no charge available, then definitely no electric field. No charge available, no electric field inside. Let me draw one more Gaussian sphere. Otherwise, let me take one Gaussian sphere here inside that, whose radius is smaller. Gaussian sphere, the flux is equal to 1 by epsilon naught times of total charge inside the total charge enclosed. When this can be written as, let me change the color. This can be written as electric field E bar dot A bar. That A is the surface area, 4 pi small r square into 1 by is equal to 1 by epsilon naught into 0. Because the inside the Gaussian sphere no charge available, so electric field inside at any point is 0. Electric field at any point inside is 0. I can write electric field which is less than of the radius at any point inside is equal to 0. Now on surface, let me take on surface. Let me change the color. On surface, let me draw the one Gaussian sphere. Just I think this is best. Red is best. Let me draw the one Gaussian sphere just outside, whose radius is almost equal to sphere. Then I can write again same formula, electric field E, which is the color again, E, electric field E on surface surface area is 4 pi r square into 1 by epsilon naught. Total charge inside the sphere is capital Q. If you simplify this, you get E is equal to Q by 4 pi epsilon naught into r square. So electric field at any point on the surface is how much? I can write K, where K is 1 by 4 pi epsilon naught, K Q by r square. When you calculate electric field at any point outside, when you write electric field at any point outside, let us take a decision, take a distance r which is greater than of the radius. Again, draw the Gaussian sphere. Once you draw the Gaussian sphere, again apply the same formula. Electric field outside, the surface area of the bigger sphere is 4 pi small r square, where radius is greater than the, radius of the Gaussian sphere greater than the radius of the sphere, nothing but it is outside the sphere. It is 1 by epsilon naught into total charge. Total charge inside the bigger sphere is also same that of the whatever the charge availability on the sphere. So from here you can write electric field is Q by 4 pi epsilon naught into r square, small r square. You can write E at any point outside, it is K Q by small r square. These three mathematical relation you must remember for the exam. In the exam you won't derive all this, but you must remember. Graphical representation also very important. So hope you understood what is conducting material. Conducting material nothing but whatever the charge you have given resides only on top surface. Now see, when r is less than of r, meaning the distance is less than the radius of the sphere, electric field is 0. On the surface, electric field is kq by r square. Outside, kq by small r square. This graphical representation is very important. If you look at the graphical representation, here see, from electric field from 0 to surface, center to surface, 0 distance to the surface, center to the surface, electric field is 0. At the surface, electric field is maximum, that is kq by r square, nothing but q by 4 pi epsilon naught into r square, and after that E is proportional to 1 by r square, so that you will get a parabola curve rule. So this graph also important. In the national level entrance exam, definitely, especially for JEE mains, graphical representation also very important. He'll give this graph, he may identify this graph belongs to solid sphere, solid conducting sphere, or solid non-conducting sphere, like that. This one is electric field due to the uniform charged conducting sphere. It is also, this expressions, this theory valid for hollow conducting sphere and solid conducting sphere. Both one and same when you look at charge distribution wise. I am not at all talking about mass, only charge distribution wise, hollow or solid conducting spheres are same. Now next one, electric potential due to uniformly charged conducting sphere. Again, electric potential. That electric potential is simple. Electric potential any point is kq by r, and on surface it is the same. At any point inside, where inside r is less than of r, it is also same that of the surface. You can ask me why. When there is no electric charge availability inside, work done to displace the charged particle from any point inside to the surface is 0. When work done is 0, nothing but the particle displaced between two points of same potential, meaning potential on surface, potential at any point is the same. Then work done to displace the charged particle from at any point inside to the top surface is 0. Why work done is 0? There is no force, there is no electric force, because there is no electric charge. So that there is a small push, very small gentle push, just to give that small speed, definitely it reaches the surface. There won't be any change in the kinetic energy. When there is no change in kinetic energy of the charged particle, whatever the speed you have given to the charged particle inside, it will continue to move with the same speed till the surface. So when no change in kinetic energy, then work done 0. Work done are 0, nothing but those 2 points are having same potential. And potential outside is kq by r. There is again small r. Now you look at the graph. In the graph, from the center till the surface, potential is the same. Potential is the same. On surface, it is kq by r. Beyond that, this is again decreases, where electric field is proportional to 1 by r square, but potential is proportional to 1 by r. There is a small change in the slope. Easily you can identify that. Now we'll move to electric field due to non-conducting sphere. Now, once you have given charge to the non-conducting sphere, the availability of the charges there inside on the surface also. Now we'll solve. See, when you look at non-conducting sphere also on surface, or if you look at the sphere outside, it is the same. Only difference is inside the electric field will be different. Once we calculate electric field inside how much, that's more than sufficient. On surface and outside at any point, it is same that of the conducting sphere. Let me take one sphere to which I have given charge q, whose radius is r. This is charge is uniformly distributed. You want to calculate electric field at a distance smaller at any point inside, where smaller is less than of the capital R. When you write in a Gauss law, according to the Gauss law, flux is equal to 1 by epsilon naught of small q. What is a small q? Small q is charge inside this sphere, smaller sphere, whose radius is smaller. Right? That we have to calculate. Before that, electric field at any point inside, surface area is 4 pi r square is equal to 1 by epsilon naught into small q. How to get small q? Here uniformly charged. So charge density is the same. Total charge by volume of the full sphere, 4 by 3 pi r cube. And charge of a sphere of radius small r, 4 by 3 small r cube. So small q in terms of capital Q is capital Q into small r cube by capital R cube. If I substitute that value here, capital Q into small r cube by capital R cube, now you left with now this gets cancelled. See, this is square and cube goes with only with 1. Then you can write an expression that is electric field at any point inside is 1 by 4 pi epsilon q into r by r cube. This is the expression for the electric field at any point inside the non-conducting sphere. Now electric field, see, capital Q is constant and capital R also constant. You can say electric field at any point inside, which is less than, distance is less than of the radius, is directly proportional to the radius. And electric field on surface, it is same, that is k q by r square. The derivation is same that of conducting sphere. And electric field at any point outside, it is also same like conducting sphere, k q by small r square. Now the graphical representation is important. Now E is proportional to R. Now moving to the next slide, in the next slide I'll show the graph. Hope you understood this. This is now electric field at the center. If I talk about center, when R is equal to 0, then electric field also 0. From center to the surface, it is directly proportional, linear increment. Now we'll see electric field at any point inside is k. This is k value, q small r by capital R cube. E is directly proportional to small r. That's why in the graph you get a straight line like this. This is a straight line, constant slope. And once from the surface at any point outside, it is same that of conducting sphere only. That is E is proportional to 1 by r square. Right? E is proportional to 1 by r square outside the sphere. Now when I talk about the potential, Now potential, again there is no big difference except inside. Now potential at inside is, that is, you can write K Q into 3r square minus r square by 2r cube. 2r cube. This is the potential at any point inside. What is the potential at center? Potential at center, when small r is equal to 0, then you can write that is K Q by r into 3 by 2. It is on surface is same that of conducting sphere, outside also same that of conducting sphere, but only thing here inside is different because of the charge availability. So at center, potential at center is 3 by 2 times of the surface. It is greater. That's why look at the graph. In the graph, it clearly mentioned that, see, this is at the center and this is on the surface. Center is greater. Center is greater, and from the surface to outside, it is again same that of the conducting sphere. That is, V is proportional to 1 by R. So this table you must remember. You must remember, practice this mathematical relations. Remember, in the exam you won't derive all this. You must remember this. Only two type of material, conducting and non-conducting. Even in these two also, only inside will be different when you talk about the non-conducting material. When you talk about the non-conducting sphere. Other than that, graphical wise, outside on surface, either potential or electric will be same that of the conducting sphere. Now we'll solve few questions based on the same concept. This is our YouTube channel. Do subscribe this, follow this. Time for IITJEE NEET. In this channel, you can find all short videos of subtopics, and you can see maths, physics, and chemistry also. You can improve your conceptual clarity by looking at the short videos. We are not putting the complete lesson into the one video. We have divided into small portions. How I have taken very small portion, that is an electrostatics, that too into only electric field and potential due to the spheres. We have ring, we have disk, other, but this in the short video to give complete clarity on the subtopic, we have chosen this. Right now, the time to solve few questions. These are the questions asked in the previous JEE mains and NEET exam. Now, this is the question. First question: concentric metallic hollow spheres of radius r and 4r. Radius is r and 4r. One second, let me tell you. Radius is r and 4r. Hold charges q1 and q2 respectively. Okay. Given that surface charge density of the concentric spheres are equal, surface charge densities are same, then the potential difference Vr minus V4r. Okay, let me write. Let me draw the picture first. This is the sphere to which I have given, whose the radius is r, and I have given charge q1, and there is another sphere whose radius is 4r, to which I have given charge is q2. Right, now charge densities are same, nothing but charge density of first inner sphere, charge density of the outer sphere is same. Charge density, surface charge density, nothing but charge by surface area, that is 4 pi r square. This is q2 is equal to 4 pi 4 r square. So this gives you I think q1 is equal to q2 by 16. I can say q2 is equal to 16 times of q1. Right. Now potential of Vr. What is the potential of Vr? Two potential due to its own charge and outer sphere also. Let me write that. K q1 by r plus K q2 by 4r. This is the potential Vr, potential of the inner sphere, minus potential of the outer sphere, K Q1 at what distance? 4r, 4r plus there is a potential to do its own charge, K Q2 by 4r. So this and this gets cancelled. You're left with what? K Q1 by r. If I take common, then I'll get 1 minus 1 by 4. 1 minus 1 by 4 is 3 by 4. This gives you a K is 1 by 4 pi epsilon into Q1 by r into 3 by 4. 4 into 4 16. 3 Q1 by 16 pi epsilon naught times of r. Which option? Option C. Option C? Yeah, option C is correct. So this is what we learned actually just a moment back. How to write a potential of a sphere. Got it? On surface only. Here in a sphere also two potentials because of its own charge, and it is placed inside the bigger sphere. That potential also. Right? Now I'm moving to the next question. Consider two charged metallic sphere S1 and S2, radii is R1 and R2 respectively. The electric field E1 and E2 on their surfaces are such that E1 by E2 is equal to R1 by R2. Two different spheres. This is a sphere whose radius is R1. This is a sphere 1, and there is a sphere S2 whose radius is R2. Electric fields on their surfaces is how much? According to him, R1 by R2. This is given data, right? Then the ratio of V1 and V2 electric potential on each sphere. What is V1? You know potential V1 is simply you can write K Q1. Let us suppose charge is Q1 which is unknown. K Q1 by R1. Then you can write V2 is equal to K Q2 by R2. Right? From here V1 by V2 he asked. So you can write V1 by V2 is Q1 by Q2 into R2 by R1. From here electric field. What is electric field? K Q1 by R1 square. That's the formula. K Q2 by R2 square, which is equal to R1 by R2. So this K gets cancelled. Q1 by Q2 into R2 by R1 whole square, simplification, is equal to R1 by R2. From here I can write Q1 by Q2 is equal to R1 by R2 whole cube. If I substitute this value here, Q1 by Q2 is R1 by R2 whole cube. Then simply you can write V1 by V2 is, see, this is R2 and goes with the 2 and denominator R2 square, and this R1 cancel with this R1 in numerator R1 square. So V1 by V2 is equal to R1 by R2 whole square. See, question. We are not very big mathematics involved in this. This is the way to solve the question. I'll show you the same problem in another method also. Got it? Now let me do that also. Now see, electric field, you know, E1 by E2. E mentioned it is R1 by R2. You know, electric field E is equal to, you know, V by the distance. So I can write V1 is equal to E1 into R1, V2 is equal to E2 into R2, correct? Then if you divide this E1 by E2, according to him, given ratio is R1 by R2. So directly you can write V1 by V2 is equal to R1 by R2 whole square. Direct straightforward you can write this, correct? Yes. Two metallic sphere is mentioned. That's why conducting sphere. If the conducting sphere, then directly you can write this E value, you know, field is equal to K Q by R square. On surface, potential is K Q by R. So from these two, you can write potential is equal to E into the radius. So from there also directly you can answer. choose which one is easy, you can follow that. Moving to the next question. This type of questions are, again I'm saying it is important, undoubtedly important for JEE Mains or NEET or CUT and JEE Advanced also. Because in this sphere, now look at, we will go to the problem first. Let me explain the problem first before solving it. Consider a sphere of radius r which carries a uniform charge density rho. A sphere of radius r by 2 is curved out. Okay, this radius is r by 2. This radius is r. It is curved out. Now take it out. As shown in the figure, the ratio of electric field at point A to electric field at point B, I mean modulus of magnitude of electric field EA bar and EB bar respectively at a point A and B due to the remaining portions. Okay, now I look at this as I have a bigger sphere whose radius is r. Let us suppose if I want to calculate electric field at a point A, I look at this as I'll calculate electric field at A due to the sphere of radius. Let me write at A due to the sphere of radius r, bigger sphere, minus electric field at A due to the cut portion r by 2. I look at this as there is a sphere of radius r and I've given one more sphere I've taken out whose radius is r by 2. That's why I've kept minus. Even the same, even write EB also. Field B due to the bigger sphere minus, why minus is taken out, right? And field at B due to the smaller sphere, right? Now let me calculate the relation between them. What are the charges? Charge on this total charge which I have given is, let us suppose Q. What is the charge here? It is, let us suppose, Q prime. Taken out charge is Q prime, right? So instead of taken out, I'll say negative charge I have given. So I have a sphere of radius r on which plus Q present, and I have another sphere whose radius is r by 2 on which minus Q prime. Instead of taken out, I'll say I've given minus Q charge. That's the logic. So you can write uniformly charged. So total charge by volume 4 by 3 pi r cube is equal to Q prime by 4 by 3 r by 2 whole cube. From here you can write Q prime is 1 by 8 times of Q. This is the relation. Now look at electric field. Now I am talking about this portion. Electric field at A due to the radius r. A is the center. It is electric field, charge density also given, so that not mention what kind of sphere. So definitely, obviously, it is point A at the center. Point A is at center, so that is 0. That is 0. And electric field due at A, because that point A is the center of the bigger sphere. What is electric field at the center of the bigger sphere? 0. Now electric field at A due to the radius r by 2. So I can say that point A is a surface. It is a point A is placed on the surface of the smaller sphere whose radius is r by 2. So K charge. What is the expression on the surface? K Q prime by radius r by 2 whole square. But this Q prime is Q by 8. So finally you can write this expression as K Q by r square. This 8, this is by 4 into 8. So simply you will get with left with 2. So I can write this is K Q by 2r square. This is the electric field at A. This is the electric field at A due to the smaller sphere and bigger sphere. Okay, got it? Now let me calculate electric field due to bigger sphere and smaller sphere at a point B now. At a point B. The point B is a surface, on surface of the bigger sphere. So electric field at a point B due to the bigger sphere R, that is radius R, K Q by R square. That's it. What is electric field? Due to sphere of radius R by 2. When you look at that point B, from the center of the smaller sphere, it is outside at what distance? At a distance of 3R by 2. Am I right? This is R by 2 and R. R plus R by 2 is 3R by 2. So I can write K, outside it is K Q prime by the distance square. Distance square is 3 by 2 R whole square. You know this Q can be written as Q by 8. So after simplification, K Q by R square. The in a denominator we have 8 and 3 square is 9. 2 square is 4, goes to the numerator. So 4 ones and 4 twos. Finally you left with K Q R square, 18 R square. This is the 18 R square. 18 R square. Let me subtract these two. Let me erase this also. That Q prime is Q by 8 already we have calculated. So simply you can write, what can I write? That is K Q by how much R square due to the bigger sphere minus K Q by 18 R square. If you take K Q by R square is common, K Q by R square is common, you are left with 1 minus 1 by 18. So this gives you K Q by R square into 17 by 18. 17 by 18. You want ratio. So what ratio you want? Electric field at a point A to electric field at a point B. Let me take that relation also. Let me calculate here. Right? That is electric field at A is how much? That is KQ by R square. Let me write here. KQ by R square, 2R square, sorry, by KQ by R square into 17 by 18. KQ by R square cancel. 2 ones and 2 nines. So finally you left with 9 by 17. So option C is correct. This kind of problems are very, very, very important. Very important. It's a time consumes, but it is most of the time, if this kind of questions asked, it is not very difficult but lengthy. But if you practice, it becomes easy. I've derived it actually, but you know the formula. Directly you can write that at electric field at the center of the bigger sphere is 0. That is on surface. Directly you can write KQ by 2R square like that. Got it? Now moving. I'm closing the session. Before closing that, this is our YouTube channel link. That is at the right time for IITJEE and NEET. Subscribe it. Do watch videos. Thank you. Thank you so much.